Hi guys, welcome back to Data Every Day. Today we're looking at a data set of big companies, Fortune 1000 companies, and we're going to be trying to predict the market cap of a given company based on a series of features about it. So we have a good number of features. We do only have 1,000 companies to work with, but it should be okay. So let's hop into the notebook. We're going to use NumPy and Pandas for working with the data. For pre-processing, we'll use the train test split function and standard scalar from sklearn. And we'll use a whole bunch of different sklearn models today, 3 different linear regressions with different kinds of regularization, a decision tree, a neural network, and then 2 ensemble methods, which will be the random forest and gradient boosting regressors. Let's go ahead and import all of that, and we'll load in the data using pandas.read CSV. So I'll go and grab the CSV file path right up here. I'll copy that, paste it in, and we can take a look. Alright, and I also want to take a look at data.info so we can see if we have any missing values. Right off the bat, I do see we have some in here. The biggest one I'm seeing is this newcomer column with that's 50% missing values because we only have 1,000 examples. So this is probably, we're just going to drop that column. Let's actually get into the pre-processing so we can figure out what we want to do. I'm going to create a function called preprocess inputs. That's going to take in a data frame. It's going to make a copy of it. And then it's going to return the data frame. For now, all it does is copy it over. So we'll pass in data to our function, get it back as x. This is the copy of the data that we'll be doing the pre-processing on. And I guess the first thing to do is to drop unused columns. Drop unused columns. So df equals df.drop. We include all the columns we want to drop in this list. Let's go through them. So we don't want the company column because these are all just unique values, and when a column has all unique values, it's not useful for making predictions because it offers no way to draw similarities between training examples. So we're going to drop company, and I also want to drop rank. The reason is I believe these were ranked. Actually, I can't be sure. Actually, looking at market cap, it does not look like the rank is determined by the market cap. Rather, it looks like maybe it was determined by revenue. As you can see, as the revenue goes up, the rank goes up as well. So we might actually consider keeping that on. I think I will keep it on because as long as, because if we have a column that's created from our target column, we have to drop it because it's leaking information about the target into our data. If it's a column that you would only have access to after you knew the results of the target, it doesn't make sense to have it in your model. But in this case, it looks like the rank is coming from revenue, which we do have access to, so we're going to keep it on there. Alright, so we're going to keep all of these because they're proper numeric information. Number of employees as well. Sector, also good. City, good. State, good. Newcomer. Now this column, actually, we saw it had 50% missing values. Half of the values in here are missing. And so at that point, it's not really a useful column because even if we fill the missing values with like the mean of the column, or the mode of the column here, we usually get worse performance because it's a lot of fabricated information. It's just going to create confusion in the model. So let's drop newcomer. And then CEO founder, CEO woman, profitable. These are I don't think they have missing values. Yeah, no missing values, and they're proper features. So previous rank. Yeah, it's interesting. Why am I not seeing any value here? So actually, it looks like maybe there's some missing values that haven't been encoded properly in this data set. Let's take a look at that. If we look at previous rank, you can see it's actually an object column. So that means it's a string column. So if we type .asType numpy.float, we should get an error and it should show us why. Okay, so there's a space in here. So if we try to replace spaces with numpy.nan and then cast to a float, it works. And then we can see how many missing values we have. So we type .isNA to see the missing values on that and sum them up to get the number. And there's 523 missing values in there. So that's also more than half missing, so we are going to drop that column. So we're dropping previous rank, CEO. In this case, every one of these is going to be different, right? So we don't need this. Website and ticker as well. These are all unique for each company. So we're going to drop all three of those. Alright, and we're dropping all these columns from axis 1, which is the column axis. There we go, that's what we're left with. And it's fairly good. We're going to shuffle this data, but the rank is a numeric variable. It's an ordinal feature that measures its place along this ranking system. Now, keeping this on, I'm not sure how good it is to keep this column on. We could definitely try it out with and without, but the reason is this is only a function of the revenue column, right? It's ranking by revenue, but revenue does a lot better job of capturing the distance between companies. The rank column does not. It treats all companies as equal, just rather all it considers is if there's more or less revenue. So I feel like I might actually want to drop the rank column, just because it might confuse the model. However, if I was going to really care about optimizing this to the best of my ability, I would definitely try out all the features, filter through anything I could, find something that works best with all different kinds of combinations. But for the purpose of this video, this is what we'll use today. Alright, so now once we have this, let's look at the missing values in here. So x.isNA.sum will return the number of missing values in each column. And it looks like we have 2 missing values in profit and 40 in market cap. So this is a little important. Because we have missing values in our target variable, we don't want to fill these in, because otherwise we'd be trying to predict missing values. We'd be trying to predict imputed values. If we filled them in, we'd be trying to predict what we filled in. That's not what we want. So if you ever have missing values in your target column, you should drop any rows that are missing with that information. So let's drop missing target rows. And we can get these missing target rows by doing the following. If we take the market cap column and we find its isNA matrix, or actually it would just be a vector here, so dot isNA, then we get a true false based, there will be a true wherever there's a missing value, and we can actually use this to index the original data frame. So here we have gotten all the rows where we have missing values in the market cap column. And then we type .index to get back the indices that we need to drop. So let's go and put this in our function. Just change x to df, and we should be good. So we have the indices. Now let's go and drop them. Missing target rows from axis 0 this time. Because we're dropping rows, we're going to reset the index. Drop equals true. Alright, here it is. We have 960 rows, so we dropped 40 rows. And let's look now. We have no more missing values here. We do have one missing value in profit. Before I move on, I want to look at x.dtypes. So there's actually some issues here. And the reason is we have a bunch of... Okay, so these object columns are fine because they actually are object columns. These are all string columns, right? From sector until profitable, those are all objects. But for market cap, we have an object type. And this should not be object, this should be float, right? Numeric. So let's figure out why this is object. Like I did before, we're going to take the market cap column, which is x sub market cap, and we're going to try to cast it to a float to see what the problem is. NumPy, as type numpy.float. Alright, and it looks like there's actually something encoded as a hyphen in there. So if we go and replace any hyphens with a missing value, then it converts to a float properly. So now let's check out how many of these do we have. So .isNA.sum. And there's 10 extra missing values. That's still okay. So let's drop those. So up here, before we drop the target rows, we're going to encode missing values. And let me just paste this in. Change x into df. So this is actually what we just want to do this part. So the market cap column is equal to the same column but with all hyphens replaced as numpy as missing values. So after we do this, then we drop the missing target rows. That should eliminate all missing values in the column. We now have 950 rows, and if we look at x.dtypes, we now it is still an object column. So what if we type .astype float after this? Now we have it as a float. Okay, good. All right, so now we can get to encoding. So the data's been cleaned for the most part. Now what we should do is get a dictionary that maps each column name to the number of unique values in the column. So we take x subcolumn dot unique, then take its length, and we do this for every column in x.columns. Actually, I just want the categorical, so I'm going to do x.select dtypes object. So just the object columns. We're going to see how many unique values are in each column. Alright, and this gives us a sense of how to encode them. So we have 3 binary variables. That means it only has 2 values. And with those it's very easy, and it's even easier because they all have the same 2 values, either yes or no. We can always just send one value to 0 and the other to 1, and that's the encoding. For the other ones, sector, city, and state, we're going to use one-hot encoding, which we'll use the pandas.getDummies function to take in one of these. Let's use sector, for example. And it will generate a bunch of 21 new columns, one for each of the original values. So each original unique value gets its own column, and a 1 in a given location represents the original value of that example. So this is a way to encode categoricals when there's no inherent ordering between the unique values in them. We can also include a prefix here. It's called sector. That will just put sector at the beginning of each column name so that we know where these columns are originally coming from. So with that, I'm going to go in here, and we're going to do 2 types of encoding. Our binary encoding, and we can just iterate through for column in and then list all the binary columns, which are these 3 here. For CEO founder, CEO woman, and profitable, we're going to take the column and set it equal to itself with the replace function called, and here we pass in a dictionary that maps no to 0 and yes to 1. And this doesn't really matter. You could have yes as 0 if you like, but we'll just do it this way. And if we run that now, all these have become numeric binary variables. Now we'll do our one-hot encoding. Here we'll iterate through for column in, and we'll list the binary variable, the nominal variables, which are these 3. For each of these, why don't we create some dummies with the pandas.getDummies function for whatever column we're on, and we'll give it a prefix of the same as the column name. And then we're going to take the dummies and add them to the data frame. So df equals pandas.concat df and dummies. So we're concatenating the dummies side by side with the original data frame along axis 1. That's side by side. And then we'll go and drop the original column from which we created the dummies. So now our encodings are all there. You can see these are all of our dummy columns on the end. And before that is all the original data. So we're almost done. Last things to do is to split the data frame into 2 parts, x and y. Y is what we're trying to predict, so that would be our market cap column. So y equals df sub market cap, and then x is the rest of the data, so df.drop market cap from axis 1. And then we'll do our train test split. So that will create x train, x test, y train, and y test. And we'll use the train test split function from sklearn to split this for us. We'll pass in x and y, give it a train size of 70%, and give shuffle equals true, and a random state. So here we give 70% of the data to the train set, the other 30% goes to the test set. Shuffle equals true, we'll shuffle the examples before we do the split, and the random state ensures the shuffle is always done in the same way. Then we'll return these 4 sets of data, get them back over here, and we can take a look at xtrain. Market cap is no longer here, so we have 458 columns. Y train is now where market cap is, so these are the target values for each of these examples. And the test set contains the other 30% of the data. Okay, so last thing to do is to scale the data. So a lot of models perform best when all the columns take the same range of values. And if we look at xtrain.describe, it's clear to see that they do not. You can see the means are all different, the standard deviations are all different, as well as the mins and maxes. So we can scale them in a few ways. We're going to use a standard scaler to scale x. So a standard scaler will shift and scale each column so that every column has a mean of 0 and a variance of 1. So we'll fit the scalar to xtrain and then transform xtrain and xtest using scalar.transform. Now, scalar.transform actually returns a numpy array, so I'm going to turn it back into a data frame, keeping the indices the same as they were, and the column names the same as they were. We'll copy this over, do the exact same thing for xtest, and that should do the scaling. And the reason I only fit to the train set here is because we want to pretend we don't have access to the test set when we're doing this scaling. Alright, and there you can see we've scaled the data, so now they all take the same range of values. If we describe, you can see their means are all very close to 0, and the standard deviations are all very close to 1. Alright, so we're ready to train. So what I'm going to do is create a sort of a dictionary of different models. I'm just going to paste them in. These are all of our models. Let me just indent them so they're all in the same line. And basically, the reason we make this dictionary is it allows us to just train them all with one for loop and then return the results very nicely. So we can say for name and model in models.items. So the items function here will return the key value pairs as tuples, so we can iterate through two at a time like this. And then we'll take each model and fit it on the train set. So model.fit xtrain ytrain. And then we'll print out a little confirmation message that says the model was trained. We're getting a warning here. I don't like seeing those, so let's just go up here. They're just convergence warnings saying the model had a hard time converging. So I'm going to import warnings and type warnings.filter warnings action equals ignore. And that, if we rerun this now, we won't see those. Okay, so we can see all of them being trained. And then let's get the results. So for name and model in models.items, we will print out, well, we can do is calculate the Rmse, which is the root mean squared error. And to do that, we're going to need a set of predictions. So ypred equals model.predict xtest. And so the Rmse is now the errors, ytest minus ypred, squared. So we square them. Then we take the mean, that's the mean squared error. And then we take the square root, that's the root mean squared error, or Rmse. And we'll print out the Rmse for each model. Sorry, this should be in a string. We'll display it to 2 decimal places and format with Rmse. Input contains missing value. Oh. Or infinity or value too large. That's very interesting. So everything's been trained. Is this the problem? Model.predict on xtest is giving us a problem. Alright, so let's look at xtest. Does xtest have any missing values? It does. Oh, we never filled that one profit column. And the reason we were able to train it is because the missing value ended up in the test set. So we never had to worry about it when we were training the models. Alright, it's a quick fix. We just go up here, and right after we drop the missing target rows, we're going to fill remaining missing values. And in this case, there's only one, which would be in the profit column. So we take the profit column, set it equal to itself with the fillNA function called, and here we're going to fill with the mean of the column. So profit df sub profit dot mean. and that should have fixed it. So let's now go down, train our models again, predict. Well, we don't have to do that. We'll just compare all the results here. Alright, and here we can see we forgot to print out the name of the model. So name plus Rmse. Alright, and it looks like our best models are definitely random forest and gradient boosting. So I want to do the same thing for the R-squared score. And R-squared score, I'm not going to calculate it myself. We can actually just get it from model.score, passing in x-test and y-test, and then pass in R2 here. The R-squared score is a measure of how much better your model is than just predicting the mean every time. So R-squared score, and let's see that. I'll actually display this one to 5 since it's less than 0. Alright, and yeah, so this lines up with this. Our best model is gradient boosting with a 0.59 R-squared and a 92,000 Rmse. So this value, if we look at y-test, let's look at y-test and look at the distribution of values in it. So y-test.describe. Actually, .plot might be better as a histogram. Okay, that's actually not helping us so much. How can this be? Is this real? Why is the distribution so small? It's saying that all the values are lying less than 0.5. Okay, let's look at y-test.describe. There might be something wrong with that. Oh, wow. Wait, these actually are super small. But that's so strange because I'm looking at this here and that's not the case. Alright, maybe there's some glitch going on. y-test.min .min is 43. y-test.max is 2 million or something. But y-test.describe is returning some very strange results, saying that the min here is, oh no, it's saying it's 43. Okay, that's fine. It's all in scientific notation. Oh, was I looking at, I didn't see that the axis must have been in scientific notation. Okay, that's annoying though because I'm trying to interpret this. Yeah, so 1e6 was that a million, right? So if this is 2 million, 1 million, and half a million, it seems like our average error is 92,000. So 92,000 here would be, let's see, that's 1/100th of a million is 10,000. This value, yeah, so that looks like 1/100th. So we're actually looking at 1/10 of this, or 1/100th of this. It's hard to say. I'm not so. I'd have to take a little more time to figure this out. But it looks like we're doing okay. If this market cap is on a scale up to 2 million, then being off by about 92,000 each time on average is not terrible, right? So it's at least doing the job to some degree. Alright, but that will sum today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.